Okay, this is the last counting example problem video, part 8. We've worked a lot of example problems, a lot, and that's just because counting is a skill that requires a lot of practice, because when you're learning it, it's really tricky when you first learn it. Okay. How many ways can you make a license plate with 3 even numbers and 3 letters? So, okay, we have a 6-character license plate, 3 even numbers, 3 letters. Okay, so with the letters, this is just a permutation with repetition, 26 letters. All right, now over here, we're choosing from a completely different group. So these are just like separate events here, completely separate events, but we're going to multiply them because they're connected. And here we want each number to be an even number. So there's, 0, 2, 4, 6, 8. There's 5 even single digits. And that's it. So 26 cubed times 5 cubed. Okay, now next, the license plate is going to have 2 numbers, 2 letters, 1 odd number, 1 even number, 2 vowels. So yeah, license plates can have different numbers of digits and whatnot, different mixtures of things. So this is going to be an 8-character license plate. So, okay, let's separate these out. We've got 2 numbers, 2 letters, 1 odd number, 1 even number, 2 vowels. Okay, so we can actually go through this. We're going to apply the product rule to all these because they're all connected, right? We want to pause whatever this is and cycle through everything. They're all, if anything changes, we want to count that. So these, we can think about it this way. These 2 numbers here can be any numbers. This is 10 times 10, any digit. 2 letters, any letters. 1 odd number, so that's 5. 1 even number, so that's 5. And 2 vowels, so A, E, I, O, U, that is also 5. And that's going to be it. This is going to be 26 squared times 10 squared times 5 to the 4th. But like, why don't we have to divide out anything or subtract out anything? I mean, how could that be it? It seems like we've got some, we're picking from the same type of or overlapping sets, right? Where here we're picking from letters, a group of 26 letters, but here we're picking from those same letters. Well, it's not 26, but we're picking from 5 letters, but there's vowels in here too, right? These are even numbers, or what is this? Odd number, even number, but these are numbers as well. So aren't we picking from these related sets? Well, not really. In some sense, yes. And obviously, yes, right? Because we're picking from numbers here and numbers here. But the first thing to think about is that they're not dynamically related. So it's not like the numbers we're picking from here depend on what we picked here. That's the first thing to note. But they still are we're still picking from numbers here that are contained here. Right? We're picking from letters here that also are in here. And so the only way that something would come into play there is maybe these couldn't be vowels, maybe. But even that wouldn't matter. You just subtract the vowels out. There really needs to be some dynamic relationship between the sets you're picking from before you have to really think about anything. Or maybe there's some constraint that makes you have to think about how those sets are related. If that's not the case, then like here, these are completely independent events. And you're just multiplying them, okay? Now, license plate with 6 letters that are not the same, so that's easy. 1, 2, 3, 4, 5, 6. 6 letters that aren't the same, that's 26 P6. 26 pick 6. There are 3 people at a party. Each person threw their coat onto the bed. When the party is over, everyone picks up a coat at random. What is the probability that nobody gets their own coat? So this is a derangement, right? They all came in, these 3 people, they came in, A, B, and C. Let's say this slot here is for coat A. This slot here is for coat B. This slot is for coat C. And they came in like this. They all had their own coat, right? And so what we're looking for, it says probability. We haven't talked about probabilities yet, so I don't know why I put this question in here, but what's the probabilities are easy if you can count. It's all just, number of successful outcomes over the total number of outcomes, things like that. So what's the total? Let's count the total number of ways that the outcomes where the people don't leave with their own coat. They go pick up their coats, and they all leave with the wrong coat. No one leaves with the right coat. So what that means is that it's the arrangements of A, B, and C where A isn't on its original slot, B isn't on its original slot, C isn't on its original slot. So that's, here is a derangement. No, B, C, A is a derangement. This wouldn't be a derangement, B, A, C, because C has their coat. So we can just manually do this. It would be B, C, A, C, A, B, and that should be it. I mean, okay, how many ways can you arrange 3 letters? It's 3 factorial, so 6. So A, B, C is 1, B, A, C is another, C, A, B is another, C, B, A, B, C, A, C, B. So there's the 6. Now, which ones are the derangements? C, A, B, B, C, A. Okay, here A has their own coat. Here C has their own coat. Here A has their own coat. Here B has their own coat. So there's 2. And so the probability would be something like 2 divided by 6, 1/3 chance. How many arrangements are there of the letters in sociological? All right, so we've got, let's see, 1, 2, 3, 3 O's, 2 L's. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 total letters. Okay, 2 I's, 1 C, 1 S, 1 G, 1 A. 3, 4, 5, 6, 7, 8, 9, 10, 11. 1 is missing. Oh, there's 2 C's. Okay, so how many arrangements are there of the letters in this word? So that's going to be 12 factorial divided by 3 factorial times 2 factorial times 2 factorial times 2 factorial. So that's, let's see, 12 times 11 times 10, all over 3 times 2 times 2 times 2 times 2. So 2 times 2 is 4, 4 times 3 is 12, and then 2 times 2 is 4. So the answer to part 1 here is 11 times 10 times 9 times 8 times 7 times 6 times 5 times 3 times 2. Okay, and how many of these arrangements are A and G adjacent? So we don't care if the A is first or the G is second. So we can just make some other letter, like a big M or something, and say that that's AG. And so now what we've got is we just take out so SOC, take out an A and a G. So there's only one A and one G, so we've got something like this, right? So with this capital M, it doesn't matter if we're not counting, or do they want us to count that? Oh, they do want us to count that. Okay, that's fine. We can still think about this like, so, okay, let's calculate the total number of arrangements of this word here. So That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 11 factorial over, and then we've got 3 factorial times 2 factorial times 2 factorial times 2 factorial. Okay, so now this doesn't care what the A, how the A and G are ordered, right? It's just this capital M here. But all we have to do is, how do we account for if, so they're adjacent, but how do we account for if they're reordered? All we would do is take, let's assume that every single snapshot had the A and the G ordered like this, every single snapshot of this. Well, we just need to pause that snapshot and switch them. So we just need to double this. That's it. So this is 11 factorial over 3 factorial, 2 factorial, 2 factorial. These cancel. I'll just leave it like this. Okay, and how many arrangements are all the vowels adjacent? All the vowels adjacent. So, okay. We've got, in that case, we can just, well, I'm still wondering, are they saying that we can rearrange the vowels? I mean, we can solve for both. So, okay, let's put the vowels into a big M. So we've got, let's see, O, 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 I, A, right? So with that, then we've got the capital M. We've got an L here, C, S, G, another L, and another C. So, okay, if we don't care about the order here, or if they're arranged, just like this, whatever, then we just calculate. So, okay, the number of ways you can arrange this. So that's 1, 2, 3, 4, 5, 6, 7. That's 7 factorial over, and we've got 2 C's, and that's it, and 2 L's. Okay. Now, if we are allowing for this to rearrange, so that all the vowels are going to be adjacent, but if we want to allow this to rearrange, we're just going to multiply this by the number of ways you can rearrange this. So that's 1, 2, 3, 4, 5, 6. 6 factorial over 3 factorial times 2 factorial. That's simple. How many ways are there to distribute 10 identical tokens into bins labeled 1 through 5? All right, so just first instinct is this is a simple combinations with repetition problem, but we still need to analyze it and make sure. It potentially could be a little more complicated because it depends, right, if the bins are labeled or not, if the tokens are labeled or not. So, all right. We've got these 10 identical tokens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the labeled bins, A, B, C, D, E. Okay? So if we did do a combinations with repetition problem here, then how would that work? What exactly would we be counting? So, okay, we could have, a certain number of tokens in bin A, bin B, right? This would be one outcome. And it doesn't matter if we rearrange the letters. It's just that we've got one or 2 tokens in bin D, 3 tokens in bin A, etc. So does the fact that we are allowed to rearrange these and we're not going to continue to count, does that take into account that the tokens are not identical? Because right now we've accounted for the fact that the bins are labeled, but we don't want to be applying counts from the perspective that the tokens are labeled. So like this is token 1, this is token 2. So, okay. If we took token 10 out of bin E and put it into bin A, and then So we didn't change anything, took token 9 out of bin A and put it into bin E. We're not counting that. We're not saying that's different. So yeah, there you go. The tokens are being treated like they're indistinguishable. So this is just combinations with repetition. We're choosing from 5 items and picking out 10. So 10 plus 5 is 15, minus 1 is 14. 14, choose 10. The Grinch sneaks into a room with 8 Christmas presents to 8 different people. He proceeds to switch the name labels on the presents. How many ways could he do this if... So first, no present is allowed to end up with its original label. Okay, well, this first part is just a derangement problem. You have... So this is person A, B, C, D, E, F, G, H. And when they come to the party, they each... Let's see, the Grinch, when he comes in, all the name labels are on the correct present before he starts switching names. And so we want to figure out how many outcomes are there to where this is completely scrambled. No capital letter is on its corresponding lowercase letter. Okay, so we do this by, we start off by getting the total number of rearrangements in general, even if people are matched up on the name labels are matched up on the right present. That's 8 factorial, right? Now we're going to subtract from that A union B, union C, union D, etc., where the set A, the set B, the set C are... So set A is all of the outcomes where the name label for person A is on the correct present. All of the outcomes where that's the case. Even if the rest of the presents have the correct name label, that's fine, as long as present A has the correct name label. So that's what the sets are. Set A, B, C, D, etc. So if we want A union B, union C, union all of the letters, then we're saying that the union of all of those is the total number of outcomes where a present has the correct name label, not including duplicates. That's what we want to subtract from this. So, okay, we start off with the number of elements in A. Well, that's going to be, we're going to multiply this by 8, choose 1, because we're going to do this 8 times, and then times 7 factorial, right? Then we're going to subtract. It's going to be 8, choose 2, because now we're doing we want to subtract out all of the intersecting pairs, A intersection B, A intersection C, A intersection D, etc. So it's 8, choose 2 times 6 factorial, because we have 2 positions are fixed. There's only one outcome. A is here, B is here, but we can scramble this 6 factorial ways. Okay, plus, and then just continue this pattern. So I've talked about the specifics of how we deal with derangements and what we're doing here. This is the inclusion-exclusion formula. I've talked about this in more detail in the previous example problems. So here we're getting all the intersections of the different triplets. There's 8, choose 3 of them, and they're all going to have the same number of outcomes where, like, let's say A, B, and C all have their present. So there's one outcome there. So now it's just, there's how many total outcomes in relation to that? It's going to be 5 factorial. And we just continue with this principle of inclusion, exclusion, alternating, adding, and subtracting like this. Plus okay, 8, choose 7, 1 factorial minus 8, choose 8, 0 factorial, and that's it. That's the number of derangements. Okay, now, How many ways can the Grinch switch the names on the labels if exactly 4 presents keep their original labels? All right, so here, what we're looking for is, so, okay, A, B, C, D, E. So, okay, we can have any 4 can be on the correct label, or on the correct part. And so, but it could be that there's different ways to have 4 correct presents, right? So it really, the number of ways you can have 4 name labels on the correct present would be 8 choose 4. You have 8 presents, choose 4, order doesn't matter. Okay, so all we need to do from here is we're going to want to multiply this by the number of derangements of 4 items. We want, so for each of these 8 choose 4, this is one outcome right here. Okay, there's 8 choose 4 of these outcomes. We want to pause on an outcome like this, and then multiply that by how many ways you can completely scramble these 4 letters here, right? So what we need is the number of derangements of 4 items. So, okay, that's going to be, you start with 4 factorial, and then you're subtracting from that. So you do 4 choose 1 times 3 factorial minus 4 choose 2 times 2 factorial plus 4 choose 3 times 3 factorial minus 4. Oh, no. This is 1 factorial. Minus 4 choose 4 times 0 factorial. Okay, but now we want to multiply this by 8 choose 4. So we've got, let's see, 24 minus, this is 4 times 3 times 2, so here's 24, minus, so 4 choose 2 is 4 times 3 times 2 is 6. So we've got 12. 4 choose 3 is 4. And this is 1. And then all of this times 8 choose 4 is 8 times 7 times 6 times 5 over 4 times 3 times 2. 7 times 5 times 2. So 70. Okay, so 24 minus 12, so plus 3, 15. So it's 9 times 70. So 630. Okay, now what about if exactly 7 presents keep their original labels? So, okay, we've got same idea in that, so we're going to take so 8 choose 7 is multiplied by the number of ways you can derange one item, but you can't derange one item. So this is going to be 0. Because you can't, if 7 presents have their original labels, then the 8th is going to have its original label. How many arrangements are there of the word parapatherapa if there are no consecutive vowels? Okay. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 characters here. Okay, let's see. We've got 1, 2, 3, 4, 5 P's. We've got 1, 2, 3, 4, 5 A's. Okay, we've got 1, 2 R's, 1 T, 1 H, and 1 E. All right. So what we can do is we can think about how if we line up all of the consonants. So, all right. P, and leave a little space between them. R, P, T, H, P, P, R, P. Okay, so there's all the consonants. And then we've got these slots in between the consonants that we could put vowels in. Because if you put the vowels in any of these slots, they're not going to be consecutive. So what we want to do is we want to start by thinking about the total number of ways we can rearrange these consonants. So let's start there. There's 9 consonants. So 9 factorial. Then we've got 5 factorial, 5 P's, and 2 factorial R's, or 2 R's. Okay. Now, we next want to think about how, so, okay, these are the different arrangements of the consonants. But for every one of the arrangements of the consonants, we want to pause and cycle through the different ways we can distribute the vowels to these slots here. So we're going to be multiplying this by, so there's different ways we can do this, but let's start with, we can have all of the vowels A, E, and we can assign a slot to them. Right? If this is slot 1, slot 2, slot 3. So how many slots? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, there's different ways to approach this, but we've got 10 slots. So do we want to pick 10 or choose 10 from here? Well, we could go either way. Let's just say choose. So we're going to say 10 choose 6. So 10 factorial over 6 factorial times 4 factorial. So with that, what we've done is we've distributed all of these vowels to the different slots, but we're not counting if we put an A here and an A here. We're not counting if we switch these two, which is what we want. However, there is the only issue is that, yeah, we're not counting if they switch spots, but if we do have an A here, an A here, an A here, and an E here, well, we're also not counting if like this E and this A switch spots, or this E and this A switch spots, and we do want to count that. So all we need to do is for each snapshot of the, so we're going to be pausing on an arrangement of the consonants and a distribution of A's into the slots, A's in the E into the slots. We want to pause all of the A's in the consonants and count if we switch an E with every one of the A's. So that's, we're counting, okay, here's one configuration, 2, 3, 4, 5, 6. So we just want to multiply this by 6. And there we go.